Testing. All right, we can get started here. Welcome everyone to this first ISTEC Distinguished Lecture for our Spring 2017 series. For those of you who are new to ISTEC, ISTEC stands for the Information Science and Technology Center here at CSU. My name is Edwin Chong. I'm the director of the center at CSU. ISTEC covers all aspects of information sciences and technologies across the campus. So we have representation from every college across the CSU campus, and we deal with everything ranging from research on information science and technologies to our educational programs, industrial affiliations, as well as outreach. And we have several activities throughout the semester, one of which is the Distinguished Lecture Series, which is what this lecture today is. The lecture will be recorded and posted on our own YouTube channel, so you can always refer other people to the video if they can't make it to today's talk. Throughout this semester, we'll also have other activities such as research workshops and fora, as well as short courses on several things, discussion panels, and so forth. Now, today we are very privileged to have a very distinguished guest here to give us our distinguished lecture for today. Professor Vikram Krishnamurthy is someone I've known for many years, but it turns out our paths were even closer than I had imagined for decades. Vikram is originally from Bangalore, India, even though he's Tamil Brahmin. He spent his undergraduate years in Auckland, New Zealand, and then went to Australia for his PhD, and he got his PhD from the Australian National University, ANU, in 1992. He was at the University of Melbourne from about 94 to the year 2002, when he left and joined the University of British Columbia as a Canada research chair professor. And since last year, he has been at Cornell University, and in particular, the Cornell Tech campus in Manhattan. And so we're very lucky to be able to get him down here to Fort Collins. I believe it's his first visit. And today he'll be talking to us about social networks and understanding social networks and controlled sensing. Please help me to welcome Professor Vikram Krishnamurthy.
Thank you for the introduction, Ed. So the title of my talk is Sensing and Decision Making in Social Networks, and this is from a statistical signal processing and stochastic control viewpoint. That's because these are the areas I work in. So just to give you a little bit of background into this talk, we'll start with some elementary definitions just to kind of set the background. So we'll define a social sensor, and this is a very loose definition, but it serves the purposes of this talk. We'll define a social sensor basically as a human who provides information about their environment to a social network after interacting with other humans. Okay? So I use the word agent and human interchangeably in this talk. So what are examples of that? Well, Twitter posts, Facebook status updates, ratings and online reputation systems like Yelp, TripAdvisor, and so on. Okay? So a human is the sensor. A sensor typically has a signal which it emits, and that is like the message which goes into a social network. So for those of us who are electrical engineers, there are immediate differences between a social sensor and a physical sensor. A physical sensor is what electrical engineers typically deal with, a radar or something which measures temperature or pressure. It turns out there are key differences between a social sensor and a physical sensor. And I've listed 4 key differences here. The first being that social sensors influence each other over a network. Typically, it does not happen with physical sensors. A temperature sensor typically will not influence a pressure sensor. But humans influence each other over a social network. So any mathematical models one develops has to incorporate that really important requirement. Okay. The second key difference is social sensors have dynamics because humans learn from past decisions. Okay. If you think about a basic undergraduate setup of a signal processing or control problem as something called a state space model, typically the dynamics are in the state equation, whereas the measurement equation, which is the sensor, is a static equation. That's typically in setups in electrical engineering, whereas it turns out social sensors are different because they are dynamic. They learn from previous decisions of the human and from other humans. The third key difference is that social sensors actually typically do not reveal full information. They quantize due to privacy or just time constraints. I mean, you typically will not say in TripAdvisor why you gave a rating of 4. You just write a sentence or 2. You wouldn't give like a 10,000 line description of that. So humans quantize information, and often those decisions are ordinal as opposed to cardinal. So meaning that it doesn't matter if a meal was $200 or $201, that would be considered as expensive. So the ordinal measurement being expensive or cheap, as opposed to the cardinal measurement, which is the exact value of how much you pay. So humans tend to be ordinal in their decision making and not cardinal. So again, one needs to capture that in a mathematical model. And another key difference is that social sensors go beyond physical sensors. The reason being that it's very hard to get physical sensors to rate a movie, for example, but humans can rate a movie pretty easily and so on. So in some sense, these are 4 key differences. There's actually a 5th difference which I probably should mention, and this is due to some of the work of economists, behavioral economists who have come up with the idea that humans have limited attention spans. Okay, that's called the idea of rational inattention. The person who came up with this, Christopher Sims, won the Nobel Prize in economics a few years ago. The idea being that when a human looks at information, there is a limited bandwidth channel between that source of information and the human brain, essentially. So again, humans are rationally inattentive. They have limited attention spans to absorb information. So all those requirements can roughly be, at least in this talk, in a very simplistic sense. One can go into much more significant generalizations. But in a very simplistic sense, this is how we're going to model a social sensor. And I want to say a few things about this. So this is like an engineering model. How good is this? Well, it's an approximation, but we'll say a lot more about it as we formulate this. So we have a signal coming to a sensor. Typically, the sensor measures the signal and noise. This is classical electrical engineering. This is a noisy measurement. You have some form of signal processing which generates an estimate. Classical electrical engineering, that's what signal processing does. It cleans out noise from a signal. Now, the non-standard part is this, that based on this estimate, the human decision maker takes a decision to optimize some local utility function. Again, that's also controversial. I'll have to describe that in more detail because not everybody believes that a human optimizes stuff to make a decision, but we'll just assume that initially, at least. And that decision goes back, affects that human and subsequent humans. Okay. More generally, the different humans interact over a graph. For example, the reds could be decisions of people who vote for one party, the greens could be decisions of people who vote for another party, and they interact over a graph. Okay. So you can imagine these little feedback loops operating over a more general graph, and that would be a more general way of modeling this sort of stuff. Okay, with that background, I just want to go to the outline of the talk. This talk is 2 highly stylized parts. Just to give you the main ideas. The first part really deals with a Bayesian approach. We're going to use Bayesian formulations to understand how do social agents, humans, learn from observations and actions of other humans. Okay? And we're going to basically focus on a specific model called social learning. And this is also in a more general domain in behavioral psychology, viewed as a special case of something called groupthink. But we're going to stick just with the idea of social learning here. And the main point is that even in a simple setup, quite amazing stuff happens. And so that's why it's an interesting problem to look into. And the second part will deal with a non-Bayesian framework, but it'll be very abbreviated due to time constraints. I'll just say a few things how, when humans interact over a very large network, what can you say from an engineering point of view, and what can you predict about the performance? So these are two parts of the talk. The first part is primarily Bayesian, very kind of stylized with knowing a lot of detail and many assumptions. The second is more general. And the key unifying theme between these two is really the interaction of sensors. And in some ways, you can view this as a more general way of saying, how do local and global decision makers interact? Individual humans are local decision makers. They're interacting with other humans. When I'm doing this simplistic local decision-making interactions, can the overall system achieve globally something useful? And that's kind of a pretty reasonable thing to look into. Okay, so we're going to go to part one now, which deals with how agents learn from the observations and actions of other agents. So part one is titled Social Learning for Sensing. And social learning itself is a pretty big area these days. It's very popular in several sub-areas. People in psychology, economics, sociology. In sociology, this is called groupthink. Computer science and engineering deal with this quite a lot. There are even popular books on this. The Wisdom of Crowds by James Surowiecki is a famous book which deals with ideas in social learning. So what I want to talk in part one are three very specific topics. The first is just give you a little bit of ideas. What is the Bayesian social learning model? Then I want to talk a bit about global sensing with social learning. And then I want to say something about what can go dramatically wrong with social learning. Okay, so here's the main setup of classical social learning. So essentially, we have the picture I had on the first page. We have some state, which is a stochastic process, evolving over time. A sensor measures the stochastic process in noise. We have a Bayesian estimator. As I told you, this part is Bayesian. So for those of you not familiar with Bayesian estimation, think of it as a way of minimizing some sort of mean square error to generate an optimal estimate. This being actually the posterior distribution. Okay, so pi k is a posterior distribution generated from your observations. And then the individual optimizes local utility based on that, and that's the local decision. Okay, that's the simple thing. This sort of setup actually arises in several problems apart from social networks. So this sort of model can be used for sentiment sensing sentiment in social networks. People use this in high-frequency trading and mathematical finance as well, and so on. Okay, I want to give you now the simplest vanilla social learning model. Just give you a few steps of the setup. So this is the only mathematics in this talk. I apologize, but it's important to have a little bit of the framework. So we have a number of agents, and we index these agents by k. So k equals 1 is agent 1, k equals 2 is agent 2, and so on. Each agent just acts once and then disappears from the picture. So k can also be considered as time. At time 1, agent acts and then disappears. At time 2, agent acts and disappears, and so on. And what do they do? So the goal of these agents, this multi-agent system, is to estimate an underlying state, okay, x. And this state is a random variable, not even a random process, just to make it really simple. It's a random variable. It doesn't change with time. It's set at time 0 randomly to one of x possibilities, okay? And so the aim is to estimate which one of these x it is. And being a Bayesian setup, there is a prior. At time 0, you know the probabilities that it's set to 1, to 2, to 3, and so on. So here's the protocol, the social learning protocol. So at time k, I'm given the prior estimate of what x is given the actions of the previous k agents. Okay? And I'm going to tell you how we can go from k to k plus 1. That tells you how you can do the whole thing inductively over time. And we're assuming that the observations people measure belong to a finite set. So what happens is at time k, I have this prior. Now I'm looking at the agent at time k plus 1. The agent at time k plus 1 gets a noisy observation yk plus 1 of the state. Okay? And yk plus 1 belongs to a finite set. It could be A and B, or 1, 2, 3, something like that. Okay? And then what the agent does is that the agent uses the observation together with the prior via Bayes' rule to compute a better estimate. Of course, it can do that because pi k contains some information about the state. Yk plus 1 contains some information. You can imagine you could fuse them via Bayes' rule in some clever way. And once the agent computes the updated posterior, it chooses an action to minimize its cost based on all the information. Let's understand what this means. This is a cost depending on the state and the action I take. I don't know the state. So the best I can do is minimize the conditional expectation of this cost given all the information I have. And this conditional expectation can be computed using Bayes' rule, essentially. Okay, so that's the point. And then what I do is agent k plus 1 broadcast this action to the next guy. And the other agents now say, okay, I have now action ak plus 1. And so therefore, I can update the posterior probability of my state given this new action to compute the updated belief. So therefore, we have a complete way of going from pi k, which was the probability of the state given the actions of the k agents, to pi k plus 1, which is the probability of the state given the k plus 1 agents. So we've gone from k to k plus 1. It's all Bayes' rule. It's pretty straightforward. Okay, so let's examine what we're doing in Bayes' rule here. So to code this up is only 3 lines in MATLAB. It's a really simple program. Yet when you run this, something remarkable happens. And so I just want to say a few things about it first. So first, let's look at Bayes' rule. So Bayes' rule here is simply saying that what I'm doing is I'm computing the probability of my action given the observation and the belief times observation given the state times pi k, and it's simply added like this. Okay. Yes?
When you say other agents, you actually want the next agent.
Correct. It could be the next agent. In more sophisticated graphs, it will be other agents. That's why I just kind of said that. But you're right. You could just consider it to be the next agent in the sequential. This is a purely sequential setup, so it's just the next agent. Okay. I want to point out something really strange about this even before proceeding with the main result. And that is this. If you think about classical Bayes' rule from undergraduate probability, you know the Bayes' rule tells you that the posterior is proportional to the product of the prior times the likelihood. That's basically Bayes' rule. The remarkable fact here is that the likelihood is an explicit function of the prior. In classical Bayes' rule, the likelihood has nothing to do with the prior. The likelihood is the probability of the observation given my state. The prior is something else. Here, the prior appears, pi k appears in the likelihood. And that too, it's a nonlinear discontinuous function because you've got an arg min in there. That is the crucial difference. And this is the reason why social learning is such a big deal in economics and sociology and so on. This non-standard update results in some pretty remarkable behavior. And let's quickly say what the behavior is. So here's a famous paper published in 1992 in Journal of Political Economy. But like everything else, it was actually reinvented. There was an original paper by an electrical engineer, Tom Cover, in 1970, who had exactly the same result. But anyway, these things happen in real life. So here's the result. If you code up these 3 steps in MATLAB and run this algorithm, you'll see after a finite amount of time, every agent chooses a decision which is exactly the same as the previous agent. So what are we saying? Rational agents completely disregard their observations and they simply parrot the decision of the previous guy. That is called an information herd. Basically, you form a herd of decisions. Actually, more technically, it's called an information cascade, but we'll call it a herd for the moment. So this is a result which happens with probability 1. It happens always in a finite amount of time. Okay? So what this means is that however smart these agents are, after a while, the agent completely disregards its observation. It simply parrots what the previous guy said. Okay? And this could be a worry, particularly if these decisions are the wrong decisions. Okay? So here are some examples which explain these sort of things. So a classical example in this has been studied a lot in economics. And here's one such example. So I'm sitting at home and I'm too lazy to look at the weather forecast. I see a guy on the street walking by with an umbrella. assuming that guy is rational. He knows it's going to rain, or he has a high probability it's going to rain. That's why he's taking an umbrella. So I say, well, I might as well take an umbrella. So now there are two people walking down the street with umbrellas. Somebody looking will say, oh, there are two guys walking down. Therefore, it's most likely going to rain, and so he takes it. And so this herding effect becomes very easily demonstrable, even though the first guy who took the umbrella could have taken it for no apparent reason at all. So the point being that it's very easy, even in this simplistic setup, to show that Bayes' rule hits a fixed point. Basically, what happens is that everybody makes the same decision. I want to explain mathematically why this happens, just a little bit of intuition as to why this entails that everybody ends up taking the same decision. And let's quickly look at this equation here. What happens is there is one step which is a little bit complex, but that tells you that, it essentially tells you, due to a martingale type argument, that this term here becomes independent of y. Okay, remember this summation is over y. After a finite amount of time, you can prove, and that part is a little bit complex, that this term becomes independent of y, so it goes outside the summation. The summation over y of p of y given x is 1. So therefore means that pi k plus 1 is proportional to pi k, which means pi k plus 1 equals pi k, which means that Bayesian update hits a fixed point, it stops. So what happens with this procedure is, after a finite amount of time, social learning stops. The actions obtained are completely useless. My decision just freezes, and everybody just parrots the previous decision. This sort of thing also has happened. There's a famous example. A couple of guys in 1995 wrote a book which received pretty reasonable, poor reviews and didn't sell very well. So what they did was they secretly bought 50,000 copies of their own book. Overnight, it became a New York Times bestseller because people started buying the book. They said, wow, this is really popular. So again, that's the idea here. If you knew exactly the action of the individual who was buying the book, you probably would say it's not a big deal, it's the author's buying the book. But you don't see that. You only see the actions. And it's this loss of information in this quantization process, essentially, which results in this form of herding. Okay, that's really the example. These guys bought secretly. And so you can ask the question, how do you deal with malicious agents who are deliberately trying to spoof the system so that you end up with the wrong decision? Okay. In these days of fake news and so on, this is really a very serious issue, where you can guide large numbers of individuals to take the wrong decision very easily. Okay, so with that basic background, what I want to talk about now are three extensions. This is something I've done in my research recently. I just want to give you the main ideas without really much mathematics. So given that social learning setup, how do local and global agents interact in decision making? That's the first question I'm very briefly going to talk about. The second question is, given that you herd, how can you delay this herding? Can you do something smart in social learning so that you delay this herding? The third question we're going to ask is, how would you price a product when individuals who buy your product do social learning? There are three important questions. All of these questions have the following big picture. So far in social learning, we talked about a sensor, a Bayesian filter, and a local utility. Now we have a controller which closes the loop. So now we're putting social learning in a control loop. Hence the term local and global decision makers. You see, the individual guys doing social learning are local decision makers. They make a local decision every time. We're trying to use those local decisions with a global controller to control the overall system. Okay, so it's an interaction of a local decision maker with a global decision maker. It's not a standard control problem because these are quantized information. These are decisions. They're not classical unquantized information. So funny stuff can happen again. One has to be very careful. Okay, a lot of this stuff of having local and global decision making relates to Daniel Kahneman, who's a very famous behavioral economist who won the Nobel Prize in economics, and his main idea in prospect theory, which is widely used by people for understanding how humans make decisions, is roughly this idea of local and global decision making. All right, so we now go on to the first example, which is how they interact in decision making. And the example I'm going to consider here is a really simple example which arises in signal processing. It's called quickest change detection. Okay, it's been done since the 1950s, but the moment you add social learning into the mix, funny stuff happens. Okay, so let's first describe what this multi-agent quickest detection problem is. We'll start with the classical quickest detection, which has been done since the 1950s. Okay. So classical quickest detection is the following problem. I have a bunch of observations, y of k, until some unknown time, tau 0, these observations come from a distribution B1. After that random time, tau 0, they happen with a distribution B2. Because we're dealing with a Bayesian framework here, we're going to assume that tau 0, this unknown time, has some distribution. Okay? Typically, it's geometric or whatever. It doesn't really matter. So this is the classical Bayesian setup. Something happens. I don't know when that happens, but I know something about the distribution of when that happens. Okay? That's classical Bayesian detection. And the aim in quickest detection is to estimate that time tau 0. Okay? You want to estimate that time tau 0 because you don't know when it happens. But you want to estimate it with a particularly clever way. Obviously, if you wait for a very long time and then you know the system has changed, of course you can say it's changed, but then you're paying a delay penalty. If you're too trigger happy and you say the system has changed before it's changed, you pay a false alarm penalty. Okay? So that's what's encoded in this cost function here. So if I announce the decision has happened before it has, so I announce the change has happened at time tau, the actual time is tau 0, so if tau is less than tau 0, in other words, I said it's changed before it's changed, I pay a false alarm penalty. If I wait too long, then I pay a penalty which is proportional to the delay after the system is changed. This is really classical stuff. So the aim now is to choose the time tau which minimizes this expression, this cost. This is a classical detection problem which has been studied since the 1950s, and Shiryaev, for example, in the 1950s, showed that the optimal solution has this really nice structure. So the horizontal axis here is the posterior probability of change. It's a probability of change given the observations I get. Okay? The vertical axis here is the decision I make. So it's very intuitive. As the probability of change given my observations gets larger, there is a particular value beyond which I say there is a change. That's the optimal policy. In fact, you can exactly evaluate what this point is, but that's not required in our case. We'll just assume that this is the structure of the optimal policy. Okay? It's very intuitive. The larger the probability, at some point I say there's a change, and then I stop. I know that's happened. Okay. Let's now do a slight twist to this problem. Instead of having observations now, we're going to do multi-agent social learning. We're going to replace these with actions, local actions of individuals. So the agents are doing social learning. We do that. So now we're doing the social learning protocol I described on the previous page, 3 lines in MATLAB. People update their belief. This is the social learning update. And this is the update of the belief. And something remarkable happens. And when we first saw this a few years ago, we were quite stunned. And you can mathematically prove this is the optimal structure. So if you look at the optimal policy here, you see something remarkable. So as the probability of change gets larger, you declare a change. That's fine. What is stunning is as it gets even larger, you don't declare a change. You change your mind. Why would that be the case? Why would it be true that if the probability of change gets even larger, it's optimal to say there's no change? It's very counterintuitive. The answer is it's due to this property of social learning. You see, again, this dependence of the likelihood on the prior, and that too as a discontinuous function, which involves an argmax, is the reason why.
It's a posterior.
Of the previous time point, sure. I'm just using it loosely. So this is the posterior prior to the previous time point. Correct. So this is a likelihood.
And what are you using for the cost function?
The cost function here is typically something which is chosen so agents make a decision which is reasonable. So it could be a decreasing cost, but they don't just pick the same actions all the time. Okay, so it'd be decreasing for one action, decreasing for the other, but the two actions have different costs. Okay. So otherwise, if one picked the action all the time, then it would be it would be a trivial thing. So it's pretty easy to show for a whole class of costs. More exactly, these are super modular costs. I can define what they are, but it's standard. In any 2x2 case, for example, it could be 4, 0, 1, and 3, something like that. So the point being that you have this multi-threshold policy. And the reason behind this is, again, because of this discontinuity. The intuition behind this is roughly this. Because of the social learning, the global decision maker who's deciding is the system changed or not has more uncertainty because agents are performing the social learning. More uncertainty reflects in its optimal policy that it's going to be not so sure as to how to declare something. You can mathematically prove this. You can show the points where jump changes and so on. But that's really the intuition behind it. So what this means from a more general point of view is that the stopping set is non-convex, because this is a disconnected set, it's non-convex. And more importantly, what it means is that global decision-making using local decisions is non-trivial. So if you have a social network of a bureaucracy, for example, where you have a manager who tells their subordinates that I want you to read something, make a recommendation, give it to the second person, subordinate makes a recommendation, and based on all these recommendations, I, at a higher level, am going to make a recommendation, highly non-trivial. You can't simply make it monotonic. It requires much more work in a bureaucracy. So this is actually pretty interesting in the sense that even a simple problem like quickest change detection becomes quite different the moment you incorporate social learning. The second question we want to address is how do you optimize social learning? So what we said a couple of slides ago was that social learning results in herding. Okay, and eventually it means that the social learning stops, the agents parrot previous decisions, nothing useful happens. Can you slow down this herding so that you might get a better estimate? The answer is yes, and I want to say a few things about that. So just to review, the reason why social learning forms a herd is because agents choose their decisions greedily. Each agent optimizes or minimizes its cost by choosing an action that results in herding and the posterior freezes. So, yes?
So instead of trying to slow it down, follow the greedy strategy and try to detect that herding is happening in certain.
You can. I'll say a few comments about it. That's a really good point. So there are things where you can change the memory, you can do random resets, several interesting things. I'll say a few things about that later. Okay, so let's consider this following substantial philosophical leap called socialistic learning. Okay? In socialistic learning, what happens is the following. Again, the aim is to estimate the underlying state, just like in social learning. But now what agents do is the following. They choose their local decision to sacrifice the local utility so that their action provides useful information to subsequent agents. You know that if you simply optimize your local cost greedily, then your action, after a while, will be completely useless to subsequent people because you're simply parroting the previous guy. So perhaps you take an action not to optimize your immediate cost. So you're actually kind of being, in some sense, socialistic in that way, but it's helpful for subsequent agents. Okay? So what you would do then is you would be a benevolent agent who chooses your local decision to minimize the social welfare cost. Not your instantaneous cost, but a welfare cost which is the sum of the cost of all the individuals, assuming there are n individuals here. Okay? So now it becomes a stochastic control problem because what you're doing now is you're trying to find a strategy or a policy which decides at each time what an agent should do. Should they be socialistic and sacrifice their local utility? Or should they be really greedy and simply choose an action which is not very useful for subsequent agents? Let's just understand it heuristically. Suppose I was estimating the state of something, and initially people were basically benevolent. So they exchanged information which was useful. They're losing out on their reward, but they're giving useful information. Once my estimate gets sufficiently close to the final value, maybe it's okay then for people to be capitalistic and completely just optimize their own costs. Okay, that's the intuition behind it. And indeed, that's what can be done. And if you do the simple version of this problem, you can show that the optimal strategy is roughly that. That initially you're socialistic, and when your estimate gets sufficiently close to the true value, then you would herd in order to optimize overall cost. And this is true in real life too, right? I mean, when you join a university as a faculty, initially the dean is really good to you, gives you a large startup fund and so on. After a while, it gets more capitalistic and wants results, and that's kind of true in most real life. Anyway, so this is sort of like the optimal strategy. So initially it's socialistic and then capitalistic. Okay? You can view this as privacy versus reputation in a social system. So initially agents are more worried about their reputation, so they reveal more information to each other, and then agents become much more worried about their privacy when things get much closer. So you can interpret this as a social group which is trying to achieve something useful. How do they trade off privacy versus reputation? This is another way of viewing that. Okay, so to summarize what we've dealt with in the second question is, how do you optimize social learning? I want to say a few other remarks about this before I go to the next slide. So think about an example of a restaurant, which is another classical social learning example. I'm a stranger to the city. I'm walking down a street. I see a restaurant which is full of people. I see another restaurant which is empty. Obviously, the restaurant which is full of people must be good, so I go there, and so that's a herding effect. The restaurant which is full remains full. The restaurant which is empty remains empty. Suppose I wanted to delay or prevent that form of herding. If I'm the owner of the empty restaurant, I could pay actors to sit in my restaurant to pretend they're customers, and that would draw in some people. So that's another way of breaking herding. That's a pricing way of breaking a herd. There are other ways of breaking herding, and one of them is, you see, this is again a case where I'm using all the past information. This pi k minus 1 is a posterior based on all the past information. What if I truncate some of my past information? I base pi k not at a1 to ak, but ak minus delta to ak, some moving window. Then too, I can change herding. So herding can be avoided, not completely avoided, but can be delayed. But you can show that herding is actually an intrinsic property of such systems. Whenever you have discrete observations, discrete decisions, you will always herd. You cannot avoid that. In this example, we've taken a sequential graph. There's a paper by Tsitsiklis and a couple of other colleagues who show that even in more general graphs, you will always herd. You cannot avoid herding. Okay, the third example. How do you price social learning? So here is a simple example. I'm a monopolist. Maybe I've started a restaurant and I'm selling my product. So every day or every time a customer buys my product, of course, one thing happens, I make money, that's obvious. But a second more important thing happens, that person reviews me on social media. So that's the social learning aspect. You see, when the customer buys my stuff, he reviews me on Facebook or whatever, other people are affected by that. Okay? So my sale has two sets of dynamics. I'm getting money, but I'm affecting future sales. And let's assume that's why social learning. The question then is, how do I price my product over time? So assuming it's a restaurant, should I start really low at a promotional price, get lots of people in, and then gradually ramp up the price? If I start ludicrously high, nobody's going to turn up, and then I'm gone. I'll make the money. So how do I do it? Well, you can prove mathematically, if the setup was social learning as I defined before, the optimal price is something called a super martingale. It's a process whose expectation goes down with time. So it means that the optimal strategy is always to start high, build a loyal elite clientele, and then gradually decrease prices. Many companies do that. Apple, Tesla, when they come up with really good products. Many good universities do that. You know, they have elite, they get good customers, and then to make a bit of money, you slightly decrease standards to get more things. So that you can actually prove this mathematically. It's at least under the assumptions here, you can prove that if you want to optimize how many people buy your product, so this is a running sum. Every time somebody buys my product, I make a money UK, the money I charge. People perform social learning. This is a public belief update. The optimal policy is to price high initially, build an elite clientele base, and then gradually decrease prices, which is kind of quite interesting. And it's, so this is something you can actually prove mathematically. Okay, so that's all I want to say for part one. I just want to make a few remarks, and then I want to quickly talk about part two. So the first question you might ask in part one, of course, is that we've done everything in a sequential graph. What happens if it's a more general graph? As I mentioned, in a more general graph, several things happen. Herding, of course, remains. It's an intrinsic property. But another interesting property called data incest happens. I want to quickly describe that. So here's the thing where maybe I went to a restaurant. So the numbers here denote event time. So this is event 1, event 2, event 3, event 4, and so on. Event 1 is I went to a restaurant, pretty lousy food. I wrote a poor review on TripAdvisor. Event 4 is somebody read my review. They were influenced by my review. They went to the restaurant, and they also found the food was bad, and so they write a poor review. Should I combine both of these to say that there were 2 negative reviews? No, because that would be biased. You see, that person was partly influenced by me. So if I take a classical expectation, simply add them, I'll be double counting myself because I influenced that person. So anytime you have loops in this adjacency matrix, you're going to be in trouble. Now, for 2 people, this is really easy to do. What if you have thousands of people and this was asynchronous, the times weren't clear? How do you unravel? In other words, how do you build an unbiased reputation system which looks at something like TripAdvisor and builds an unbiased system which unravels this data instead? It can be done. There are optimal algorithms for doing that based on the structural adjacency matrix. Why is this important? Well, a 1-star increase in Yelp results in almost 5 to 9% increase in revenue. So it's a big deal. I mean, you cannot afford to have this form of data insights ruin business. Again, these days with fake news, this is a big deal because a propagation of fake news reinforces itself very quickly. And can you build an unbiased blog which actually unravels this biasness in fake news? And this can be done mathematically, at least under certain assumptions. The second point I want to mention. So right through in social learning, we said that individuals were greedily optimizing their own utility function. That's controversial. People that say individuals don't optimize utility function. Well, you can treat this in many ways. One of them is to say that humans are risk-averse decision makers rather than expected minimizers. What does that mean? The expected value is an additive operator. That is, it's known mathematically, it's from undergraduate days, that expected value of x plus y is expected value of x plus expected value of y. Risk-averse measures are sub-additive. So that means it's less than equal to the right-hand side. So it's a generalization of expected values. It is well known that humans are typically risk-averse decision makers. You do that when you teach an undergraduate class in probability. You go to the first class, tell a student, I either give you $10 for sure, or I flip an unbiased coin, and if it's heads, I give you $100. Now, of course, unbiased coin, I give you $100 if it's heads, the probability of having that is half, so your expectation is $50, as opposed to giving you $10 for certain. Most students would take the $10 for certain. They're risk averse. That's kind of classical human decision making. So you can actually reformulate this entire social learning framework by replacing this expectation operator by a risk-averse operator. Okay? In particular, there's something called coherent risk measures which have been developed by Rockefeller, which is a really powerful thing which is used in math finance. One of those big risk-averse utility functions is called CVAR, conditional value at risk, which is a big deal. And you can redo all of this social learning with risk-averse measures. And you see something really interesting there. If individuals are risk-averse, they herd more because there's security in numbers. They herd more on safer decisions. And you can actually see that in what you do. Okay, so that's another point. The third point is, okay, all this is mathematics. How does it relate to the real world? Well, we've done real data experiments on this. We collaborated with the psychology department at UBC in 2015. Every second-year student, probably about 800 students, had to do the following kind of visual task, perceptual task problem. Essentially, students were taken as pairs, so the 2 students doing this experiment at any given time. Each student is given a sheet of paper with a bunch of circles on the left-hand side, a bunch of circles on the right-hand side. The student has to decide which side has circles with average larger radius. So the answer is either left or right. So say I say left, I tell it to my partner looks at his or her sheet and says, oh, maybe it's right, comes back. Until they converge to the same decision, either left or right. If it went on for more than 20 goes, we stopped the experiment. Okay? So we did this for over 800 students, and we found that, and this has been done by many people, these sort of experiments, that data insights happen almost 79% of the time. That if you told somebody something and that person confirmed it back to you, of course you would stop it. You'd say, oh, it's really good and I must be right. And so this caused individuals to modify their actions almost 21% of the time. So many other people have done these sort of psychological experiments to show that herding and data interests are very standard in human decision making. So it leads to the problem, human interpretation of data. Suppose a couple of security guards are looking at a television screen. Should they be in the same room and discuss what's going on? The first security guard says, oh, that looks suspicious. Should the second guy say, well, if I don't say it's suspicious, do I look like a fool? If I do say it's suspicious, that reinforces the first guy's belief, and very quickly things can go wrong. So how do you do that? It actually is pretty non-standard. Okay, the final question which I want to state in part 1 is, in classical social learning, we assume that the order of agents was known ahead of time. Agent 1 acts, and agent 2 acts, and agent 3 acts. What if that wasn't done? So here is a little picture. There are 4 people here. Let's assume that guy has the highest reputation, good reputation, low reputation, 0 reputation. Okay, there are 4 people sitting around a table. In which order should these guys speak in order to get the best decision? If these were censors and they didn't talk to each other, of course you would first poll the most high quality sensor, the one with the highest signal to noise ratio and so on. But not so amongst humans, you see, because suppose these 4 guys were sitting around a table and we're trying to decide, should we hire a particular individual? If the senior most guy says, this individual is lousy, we should not hire him, that's going to affect what the junior people say. It's going to unduly affect them. If the junior guy speaks first, well, what the hell does he know? He has such a large variance, he doesn't know anything. So in which order should one speak? This is a highly non-trivial problem. It's known that the seniority rule is typically not optimal. In some cases, the anti-seniority rule is optimal. For example, the US Supreme Court, when justices release their decisions, they read it in anti-seniority rule order. So the junior most judge speaks first, so he's not overly kind of burdened by more senior people. So this is a non-trivial problem. It actually is an interesting problem. So, you know, as academics, people like to talk about group projects among students and so on. There's research done at UC Berkeley Haas School of Business, which shows that in 94% of groups, the final answer was simply the first answer suggested. And the first answer suggested is typically by the most dominant person in the group, not the wisest person in the group. So oftentimes, group dynamics aren't as good as one thinks they should be. Okay, so there's actually a really good paper on information aggregation, and there are many papers in this area tomorrow. Okay, to summarize part 1, what we've said is that social learning results in herding, information cascades. Individuals end up blindly imitating others. The more general saying of this, based on James Surowiecki's book, is group behavior is not necessarily wise, that larger crowds actually reduce diversity. Okay? It's different to classical statistics. In classical statistics, if all your observations were independent, the more observations you get, the better off you are. But the more correlated humans you get, because humans affect each other, oftentimes the less diverse you are in many ways. The final point I wanted to mention was rational inattention models. As I mentioned, that all this stuff can be generalized to the case where humans absorb information in a limited way, and you can actually model that. We're rapidly running out of time. I just want to briefly talk about part 2, but I just want to say one more thing in part 1 before we leave. So herding can result in really complex behavior. In fact, there's this well-known saying from Yogi Berra that nobody goes there anymore because it's always too crowded, and you can actually come up with herding using, you can show herding gives you that kind of behavior. It's a logical paradox in some sense. Okay, quickly part 2, because we're running out of time. I just want to say a few things about part 2. So in part 2, very briefly, you can consider the case where now you have lots of agents interacting over a very large network. In part 1, the network was small, and we assumed agents were rational, they were Bayesian. Now we're assuming this is a really large network. For example, a typical thing like this could be the sentiment on, say, an Apple product. Okay, so Apple has released a particular iPhone. The sentiment is something which is changing over time. It would change, for example, if Samsung releases, a competitor releases something, the sentiment of a company changes. So sentiment analysis is a big deal in social media. So theta n is some random process, the sentiment. How do you measure the sentiment now? This is a big social network. What you do is you kind of query some individuals in the social network. You can't talk to everybody on Facebook, only a few people. And based on that, you want to estimate what the sentiment is. So it is kind of similar to the part 1 of the talk, except now this sensor is a random evolving graph where you're polling certain nodes. So, you know, there's a lot of work done in this area, and I don't want to go too much into these, but just to say that sentiment analysis is a big deal. I mean, even for the stock market, people have showed that if you can use sentiment analysis, you can sometimes do much better than what mass finance can today, just by looking at what people are going to say in Twitter and so on. So very briefly, I just want to say a couple of things. First thing is, if this is a large graph, as an engineer, how do you build a tractable model? I mean, first of all, engineers like to model things in a tractable way. The answer is you can build a tractable model. There's something called mean field dynamics, which essentially replace this horrible combinatorial object where people either say yes or no when you're polling them, by a differential equation. Okay? So you can approximate this horrible growing combinatorial object by a differential equation, which is called the mean field dynamics. Okay? So now you can imagine the mean field dynamics, which is driven by the sentiment you're wishing to estimate. You're polling certain individuals, so you're measuring this estimate in noise, and so your question is, how do you estimate measurement given this noise? This is a classical signal processing filtering problem. The point being that once you've formulated the mean field dynamics, it's a tractable problem to solve, and you can solve this. Okay? So this can be done quite nicely. And once you can do that, you can imagine actually that the sentiment estimator is used to interactively advertise to change the sentiment. That's what people do. So when Apple knows, for example, the sentiment is going down, they're going to interactively advertise more and more. So this could be an advertising strategy to control this whole thing. Okay, so this sort of stuff has been widely studied. I don't want to say too much. I just want to say one more thing before I stop. So one of the steps in that was we were going to sample individuals in the social network. How do you sample individuals in the social network? Well, think about the latest elections in the United States for the president, and they were horribly wrong in terms of the polls. Why was that the case? Because they use something called intent polling. In intent polling, you ask people, who will you vote for? That's usually almost always wrong because you don't poll sufficiently many people. There's something called expectation polling where you ask people, who do you think will win? The intuition is that when you ask people, who do you think will win, they're going to average not only with respect to themselves, but all over their friends. So they're potentially a larger sample. So you'd imagine expectation polling is more accurate. It typically is, but not always. I mean, it depends on the structure of the social network. For example, if this is a red guy, is red Republican or Democrat in the US? I don't know, I'm a newbie here, but whatever. This is Republicans, right? So imagine this red guy was a friend of all these blue guys. If you did expectation polling, each blue guy would refer to the red guy, so it's going to be horribly biased. So it's not always true that expectation polling is better, but in many cases it is, and you can use the graph structure to unravel that and make it better. The only other point I want to say in terms of polling is that there's a well-known result in sociology which says that on average, your friends have more friends than you do. It's called the friendship paradox. You can Google it up. It was a paper in 1991 written by Field. By Feld. It's a well-known thing. Actually, it's very easy to prove mathematically. It's a couple of lines. But on the average, the mean number of friends is smaller than the mean number of friends of friends. So always people have an inferiority complex that their friends have more friends than they do. And so you can imagine now you're going to ask, who would your friends of friends think was going to win the election? And that would be another way of thinking about this sort of polling strategy. And you can do optimal polling. Okay, so just to summarize, part two was very brief. I just mentioned how you might be able to poll a bigger network, how you can formulate a bigger network as a filtering problem, and possibly estimate sentiment. Okay, to summarize this overall talk, we just had two parts. Part one was highly stylized. We spoke about few agents interacting. There were things like herding and data incest, and we spoke about how you could optimally price things. Part two, which was very brief, was simply trying to estimate sentiment and how you would sample a network. I just want to say this talk is highly simplified. We've omitted several important details. But just for the idea of giving you the key main ideas which kind of drive this thought process. In case you're interested, here are some papers of mine which deal with similar stuff. Thank you.
I'll take one question. All right, yeah, we are over time a little bit, but there's one more thing I wanted to do just as a token of our appreciation for Professor Vikram Krishnamurthy's talk. We have a plaque here to present. I'm going to read from it real briefly. It says, presented to Vikram Krishnamurthy in appreciation for your Information Science and Technology Center ISTEC Distinguished Lecture, Colorado State University, February 27, 2017. Thank you all for coming. A quick announcement. Professor Krishnamurthy will give another talk tomorrow at 2 o'clock in the Laurie Student Center, room 370, 3 something. I'm sorry. It's in the announcement you all got by email. That's a more technical talk, a little bit more focused.
Could you announce the
Okay. On Friday, there's at 10 a.m. there's an HPC forum where we will talk about the new Summit system at CSU, which is a supercomputing system that we have in collaboration with CU Boulder. It's going to be held right here in the event hall. 10 a.m. Friday. Thank you all.